Kia ora koutou, no mai, haere mai. Welcome to lesson 22 for introductory physics. This lesson is going to start the topic of thermal physics. So what we're going to look at first is what temperature actually means in a physics sense, and then we'll expand on that a little bit along with some calculations and formulas. So to start with, our goals for today are to define temperature, internal energy and heat, convert between Celsius and Kelvin, and to describe and calculate the specific heat capacity of a substance. That's a concept that can be a little bit confusing, so I do recommend taking the time to make sure you understand specific heat capacity, how to calculate it, and what it means, slightly more than you may find you need on other topics. So to start with though, what is temperature? In everyday life, we're constantly talking about temperature. You know, it's hot outside, it's cold outside, the fridge keeps our food cold, the freezer keeps it colder, then the oven heats things up. We're always talking about temperature. It's just a part of our life. But what does it actually mean for something to be hot or cold? When we're talking about it in everyday life, what we're talking about is relative temperature. This fridge keeps things colder than it does outside in the open room. The air conditioner keeps your house cooler than it is outside. The car gets hot when it sits out in the sun. And we're just talking relative. The car is hotter inside than it was when you were out in the atmosphere before you got in the car. So we're just talking relative. It's cold today just means it's colder in the atmosphere than it was on a previous day, or the average temperature. It's colder than that. So it's all very subjective. There's nothing scientific or very specific about that, which is not useful for us as physicists. One of the simplest examples, and I absolutely recommend doing this if you've never done it, it's quite a fun thing to muddle your brain up a little bit with this experiment. Experiment's a bit of a strong word, this little activity. So if you haven't done this, I do recommend you have a go if you have the equipment. So all you need is 3 bowls. They don't have to be big fancy jars like shown here. They can just be regular old bowls that you can fit at least your fingers in, if not your whole hand. And what you want to do is you want to put water into all 3. In one of them, you want to add some ice cubes so that it becomes very cold water. In one of them, you want to just leave it at room temperature or leave it to warm up to room temperature if it starts slightly colder. And in the third one, you want to put hot tap water. Now, you want to be careful not to burn yourself. You just want to make it hot so that it feels very hot, but still not uncomfortable to put your hand into. And what you do is you put one hand into the hot water and one hand into the ice water, and you just leave them there for a few moments so that they start to adjust, not really quickly, but just leave them there for a little while. And then take both hands out and put them both into the room temperature water. And what that will show you is that the room temperature water will feel cold to the hot hand and hot to the cold hand. And that's because your temperature sensors, the way that you detect temperature, is relative. If your skin goes from one temperature to suddenly a lower temperature, it doesn't actually care about what the absolute temperature is. All it says is, hey, this is colder than it was before. You should be aware of this temperature change. That's the message that your brain is getting. And so because it just feels relative, it means we are no good as temperature detectors. We can be detectors for some things. We can monitor motion or how many times an event occurs. We're good at observing scientific things in that sense, but we're not good at observing scientific temperatures. And this is a good demonstration of that. Recall that we said particles are moving in a gas. Right? They're flying around, they're bouncing off the walls. That's what atmospheric pressure is. That's what any kind of gas pressure is. If it's moving, that means it has kinetic energy. If it's moving faster with more kinetic energy, then it will provide more collisions. That kinetic energy is temperature. That's what temperature is. Temperature is how much kinetic energy the individual atoms or molecules making up some substance have. That's all temperature is. The hotter a substance is, the higher its temperature, the more kinetic energy all its particles have, the faster they are moving. So a hot gas, which could just be the air on a 30-degree day, is going to be faster moving. All the molecules are faster moving than in a cold gas, which might just be the air on a 5-degree Celsius day. So the kinetic energy of all the particles is going to be different, and that is what defines the temperature of a gas. But it's not just gases, it's the same for solids and liquids. In liquids, remember, the particles are still moving around. So if the particles are still moving, they still have kinetic energy, so they can just move around in the body of liquid a bit faster than they would in colder liquid. So it's the exact same concept with gases and liquids. So gases, they're flying around the room faster. Faster speeds, higher kinetic energy means higher temperature. In a liquid, they're moving around within the body of liquid. So they're not free to fly off into the room, but they can move around within the liquid. And exactly the same, faster moving particles within the liquid means higher temperature. Now, this isn't talking about flow. This isn't saying the fluid is flowing. So a river might be flowing very fast, but still be very cold. If you've ever been in a mountain river, then you'll be aware of that. You can have flowing water while still being very cold. This is talking about the movement within still water. So the movement of particles relative to all the other particles. If you've got flowing water, then they're all moving together. So relative to each other, they're moving very slowly, even though all together they're moving quickly. Temperature is talking about that movement relative to each other. So if the whole river is flowing and the particles are only just moving a little bit relative to each other, that's going to be cold. If it's flowing and they're all moving very fast relative to each other, that's going to be hot. Or hotter, not necessarily hot. This little GIF here shows you a couple of drops of ink into cold water on the left and into hot water on the right. And what you'll see is that the hot water, the dye spreads around, it moves very quickly. And that's because, remember the Brownian motion, the motion of the seed sitting on the water. It's the same kind of idea here. All the water molecules that are moving around in the water bounce into the dye molecules, and as they bounce into the dye molecules, those dye molecules get sort of spread out throughout the water. In the cold water, you can see that the dye molecules are pretty much just going down slowly. There's a bit of spreading out, a few little bits where it sort of shoots off where they've been pushed around by the water molecules, but there's not a whole lot of motion going on. But in the hot one, you can see that it very quickly spreads out, and that's because all the water molecules are moving relative to each other very quickly around within that body of water. And so that hot temperature water, the molecules all moving faster, we can see the effect of that by looking at the dye that's been dropped into it. I mentioned that the same thing is true for solids. How does that work then? The atoms in solids, we said we're stuck in place. They can't move. So what does temperature really mean in that sense? Well, they can still move, just not very far. The bonds are kind of like springs. Remember, we talked about the bonds being like springs. The idea of an atom moving when it's stuck in a solid is just the idea that it can move a little bit against those springs. So you can imagine it pushes this way against that spring and stretches that one out a bit, but then it can't go too far, so it'll bounce off in a different direction and then a different one, and it'll just sit there sort of moving around in that space. But it can still actually move, so it can still have some kinetic energy. If you imagine it bouncing directly back and forwards, then obviously its kinetic energy will slowly decrease, but the elastic potential energy of that bond will increase, and then it'll convert back to kinetic. So we're talking about that sort of the idea of the average kinetic energy as it bounces around inside its little space that is defined by those bonds. The temperature of a substance is the average amount of kinetic energy its particles have. There is a formula that relates kinetic energy to temperature. We're not going to bother with that formula specifically. We're just interested in this relationship between the two. Feel free to look it up. It's not complicated, but it's just a little bit extra, and we didn't really need it for this understanding that we're going for. So the average amount of kinetic energy of all the particles in a substance is what we call the temperature of the substance. But it's important to remember that the molecules of the substance will not all have the same kinetic energy. Some will be moving faster, some will be moving slower. The average is what determines the temperature. Now remember that these are tiny, tiny atoms, and we're getting just far too many collisions to count, numerous collisions constantly from these particles. So it doesn't really matter if they vary slightly. Because there are so many of them, it's going to average out very easily. And that's why you don't suddenly feel a hot spot on your skin and then a cold spot on your skin from the air, because the averages are spread out very well because there are so many of them, right? If you roll 2 dice, then you'll quite often see a 1 or a 6, and you'll notice the 1 or the 6. You might roll 2 1s and you get an average of 1. You might roll 2 6s, get an average of 6. That's going to happen occasionally. If you roll 1 billion dice, your average is pretty much always just going to be 3, right? Between 1 and 6, or 3.5, I guess. It's always going to be 3.5. That's the same thing with these air particles or with any gas or liquid molecules. There are so many of them that the average is all you ever really notice. You can't really notice any giant fluctuations as a result of this range of temperature. But it's important to remember that range is still there, as we will see when we talk about phase changes. So think about atoms as tiny balls. Remember, we did a lot of study on billiard balls, just the idea of collisions between two perfectly elastic balls, and they would collide and bounce apart. The kinetic energy would be conserved, the momentum would be conserved. Temperature and gas molecules, we treat exactly the same way. We think of those particles, those atoms that make up the gas in our atmosphere or in any gas or any liquid, we think of them as little billiard balls moving around. If one hits another one, they might change their relative kinetic energies. They might essentially swap their kinetic energies, but the total amount of energy is going to be the same. The total amount of energy in the system is going to be the same. So therefore, the average kinetic energy and thus the temperature is going to be the same. So a system can't gain or lose temperature, right? It can't get hotter or colder if it's just on its own. There has to be some net external supplier or subtractor of energy for the temperature of a substance to change. And that's just conservation of energy, which we've already discussed. When we touch something hot, we're burned. This is simply our cells receiving too much energy from the very energetic particles in that object. So you put your hand on a stove element, please don't actually do that. But if you were to do that, then the element particles, the particles in the stove element are going to be bouncing around very quickly. Remember, they're in a solid, so their version of kinetic energy is just moving around on the spot, but it's still kinetic energy. And if you put your hand on top of that, then the ones on the surface are going to bounce into your cells, into the atoms making up your hand, and they will receive too much energy and they will burn. They can break apart or die, and that's what burning is. Or proteins inside the cell can become deformed. There's a whole bunch of different things that can occur when you get burned, but essentially it's not good, right? I mean, our cells receive that much energy, it's bad, and we get burned. So thinking about temperature as those collisions between particles is very important. We will talk about temperature transfer, how that energy is transferred between things as well. And again, keeping that in mind about just particles colliding into each other, kind of like those billiard ball collisions, will help you understand all of that process. In a solid, the atoms are all held in place. The more energy they get, the more they will jiggle around. Eventually, the atoms will get enough energy to actually break their bonds. Just like if you pull too much on a spring, that spring will break. The same thing will happen with the atoms in a solid. If it gets too much energy, pulls too hard on that bond, it can actually break the bond. And when the atoms break their bonds, that's when they become a liquid. They're now no longer held in that one exact place. They're free to move around between all the other atoms, and we have a liquid. So that makes perfect sense. If we heat up a solid, we give the atoms too much energy, then they will break those bonds and they will flow around and become a liquid. And we're all familiar with that, the idea of melting a solid. The exact same thing happens with a liquid. If you give the atoms in a liquid too much energy, eventually they'll be able to overcome the attraction to those other liquid atoms, and then they can fly off into the atmosphere. And that's what we see with boiling water or any kind of evaporation, right? We give some atoms within that substance too much energy, they break the bonds with their neighboring liquid molecules, or not neighboring ones, any liquid molecules, because it's just a liquid. They're just attracted to any of them. They'll break those bonds and fly off into the atmosphere and become a gas. We'll come back to phase changes. In lesson 24, we're going to talk a little bit more about phase changes. We're going to also look at some more examples of just temperature changes in general, expanding on what we're about to look at. For now, what we want to know is that there is a melting point where a solid turns into a liquid, and there is a boiling point where a liquid turns into a gas. And so we want to be aware that there are those temperatures where that will occur. For a specific substance, this always happens when atoms have a specific amount of kinetic energy, i.e. at a certain temperature. So for water, we're all familiar with water freezing at 0 degrees Celsius. It also melts at 0 degrees, depends on whether it's getting colder or warmer, obviously. And it evaporates or boils at 100 degrees Celsius. So at 100 degrees, then liquid water will turn into gas water. And the Celsius scale, which you may not be surprised to learn, was based on those two temperatures, the 0 and the 100, which is what we're about to talk about, measuring temperature. So far, we've talked about hotter and colder. Right? And I just mentioned that we have 0 and 100 as our reference points for water, but how do we define those reference points? How do we define 0 degrees Celsius? Well, that was exactly how it was defined. Celsius, Anders Celsius being some guy back in, I've forgotten the date, so I'm not going to guess it, but you can look it up. Back in the day when they still had to have paintings, not photographs. He decided that he wanted to measure temperature on a scale. He wanted to do science based on it, and that meant we'd be getting quantitative, not just qualitative. So he came up with a scale, and he chose to use the 0 degree Celsius, the freezing point of water as one reference point and the melting point of water as another reference point. And he decided that for the sake of the metric system, there would be 100 steps in between those 2 points. So that was great. Actually, I'll just add a little side historical note. He put it back to front. He said 100 would be where water freezes and 0 would be where it boils. And so as you get hotter, you're actually getting lower temperature value, which did make a lot of sense. Shortly after his death, it was renamed and rescaled to be the Celsius scale the way we know it now. But Lord Kelvin said, hey, if temperature is how much the atoms are moving, then if you keep taking away energy, eventually the atoms will be perfectly still. If you keep taking energy off the atoms, and that energy is how much they're moving around, how much they're jiggling around, then eventually they'll stop jiggling, right? They'll just be stationary. That's not an actual quote, but eventually that was the idea. Eventually you could get these atoms down to being so cold that they would sit there perfectly motionless. And this point of no energy, he called absolute zero. The idea that you can't get any less energy than that because you've got none at all. It's the same idea in our big scale systems where we're talking about something like a truck. If it's just sitting there not moving at all, that's the lowest energy it can get. You can't get negative energy. If it starts moving backwards, that's still positive energy. It's just moving in the opposite direction. If it starts moving forwards again, then it's still positive energy. So you can't get less than just being motionless, just sitting there. He said the exact same thing about atoms in a substance, the idea of temperature. They can cool right down and they can get to zero energy. So there must be some 0 point where they have absolutely no motion. He called it absolute zero, and that is the Kelvin scale. So the Kelvin scale uses this absolute zero as its 0 point. So negative temperatures just don't exist on the Kelvin scale. They're not a thing. They cannot exist. But the Kelvin scale still uses the same step size as the Celsius scale. So he said, right, well, that 100 degrees between 0 degrees Celsius water freezing and 100 degrees Celsius water boiling, those 100 degree step sizes, that's fine. We'll stick with that step size. We'll just shift our 0 point so that we're starting at absolute zero instead. And the reason that's good is because it makes it very easy to convert between Celsius and Kelvin. If you've got a temperature in Celsius, you just add 273 to make it Kelvin. So 0 degrees Celsius is 273 Kelvin. 100 degrees Celsius is 373, not degrees, is just 373 Kelvin. Kelvin doesn't have the word degrees in front of it. Celsius is degrees, Kelvin is just Kelvin. Room temperature, which is averaging around about 21 degrees C, is around about 294 Kelvin, and 0 Kelvin, so absolute zero, is negative 273 degrees Celsius. So you cannot get a lower temperature than 273, it's actually 0.15 degrees Celsius. You can't get lower than that. That is where the particles have no energy, so you can't get any colder. The important thing to note when you're doing any kind of thermal physics, when you're switching between Celsius and Kelvin, is that the step size is exactly the same. Remember how I said Lord Kelvin said, all right, 100 degree steps between 0 Celsius and 100 Celsius. That's fine, we'll stick with that step size. That means that an interval or a temperature difference on the Celsius and Kelvin scales is exactly the same. If you heat water up from 20 degrees Celsius to 30 degrees Celsius, you've increased the temperature by 10 degrees Celsius. In Kelvin, if you convert both the initial and final temperatures to Kelvin, you've gone from 293 up to 303, which is still 10 Kelvin. So the step size is 10 in both scales. So it's important to remember that if you have an actual temperature, so if you said 20 degrees Celsius as the temperature of a room, then you would need to convert it to Kelvin in order to get the actual temperature in the room, which would be 293 Kelvin. But if you've got a temperature difference, if you say this object has increased in temperature by 15 degrees Celsius, then it has also increased in temperature by 15 Kelvin. There's no conversion needed. They have the exact same step size. So it's important to realize when you're working through a problem or looking at a scenario, whether you are talking about an actual temperature, a temperature reading off the scale, in which case you will need to convert between Celsius and Kelvin, or whether you're talking about a temperature interval, a temperature difference, how much a temperature has changed by, in which case you don't need to convert. The Celsius and Kelvin values will be exactly the same for that difference. That's an important step. Hopefully it will become clearer as you start working through some examples, but it is something to keep in mind. So just to really reiterate this, because it is a tricky point for a lot of students as you're getting familiar with the Kelvin scale. If you've used it before, you're probably already familiar with this. If you haven't, this is one of the sticky points. A specific temperature is different on the Celsius and Kelvin scales, but a temperature difference is the same on both scales. All right, so specific temperature different, temperature difference the same. This part of the lesson is going to be on heat and internal energy. So we've been talking about temperature, but what do we mean by heat? Suppose you give a substance some energy. Since the atoms will start moving around more, you expect the temperature to increase. That's what temperature is. Temperature is the kinetic energy of the atoms. If you give the atoms more kinetic energy, then they are going to get faster. What else happens? Does all the energy become kinetic energy? There are actually different ways a substance can store the energy. If you give a substance some extra energy, it's not all going to become that kinetic energy that we think of as temperature. It's not all going to become that. Some of it will go off and become other forms of energy. So the types of energy are translational kinetic energy, which is the temperature-related kinetic energy that we've been discussing. Translational just means moving through space, which is the idea of that kinetic energy as it moves through from one point to another point. It moves through space along some pathway. That's our traditional idea of kinetic energy, right? So that's what temperature is, translational kinetic energy. But that's only one type of energy that a substance can have inside it, internal energy, energy within the substance. The other types are chemical potential energy, which is energy stored in the bonds between the atoms. So that is extending the bonds. So the idea that in a solid, one atom is held in place next to another atom by a bond. If you give the substance some more energy, then the length of that bond, the average position between the two atoms might increase. And that's increasing that chemical potential energy. Rotational kinetic energy is the idea of an atom spinning on the spot. For a single atom, that doesn't really mean much. But if you've got a molecule, which is two atoms joined together, like a water molecule is actually three atoms joined together. You've got an oxygen connected to two hydrogens. If that whole molecule starts rotating, then it's got no translational kinetic energy, so it doesn't have that temperature. It doesn't have the translational kinetic energy, but it's got rotational kinetic energy. So that's not temperature, but it's still a form of energy that these substances can have. And finally, vibrational kinetic energy. And that's the idea of vibrations within the particle. So keeping in mind that water molecule, if you've got the oxygen and two hydrogens, and the hydrogens start vibrating relative to the oxygen, so that the whole molecule is still in the same spot, it's still not rotating, but it starts vibrating within itself like a little spring system. It's just sitting there oscillating. That's vibrational kinetic energy. Now, it can be confusing, as with many things, when we're talking about temperature and trying to visualize substances as being atoms. It can be confusing to think about vibrational kinetic energy in this sense, because we've already talked about the idea that in a solid, temperature means an object, an atom vibrating in its little space that it has in the substance against all the bonds around it. And here we've just said that vibrational kinetic energy within a molecule is a different type of energy, and it is. So I apologize, you just have to get used to that idea. In a solid, the atom's vibrating on the spot. I'll often try and call it jiggling or something rather than just vibrating, because we use vibrating in this other sense. But the atom's jiggling on the spot. That is translational kinetic energy. It is the kinetic energy that the substance has. That is the temperature. Whereas when you have something like liquid water, the vibrations that occur with the bonds, it's a similar idea of this vibration, but in this case, it's not temperature because it's not causing the whole molecule to move, and that's what the temperature would be in that case. So altogether, all these different types of energy that we have within a substance are called internal energy. This is completely different from the energy on the big scale that we think about. So go back to thinking about that truck that's not moving, so it's got no kinetic energy. There's still internal energy. The atoms inside the truck that make up the truck and everything in it, they are all moving. Even if they're just at room temperature, which is 21 degrees Celsius, remember that that's actually 294 Kelvin. So that's quite a lot of energy compared to having none at all. So they've still got all this internal energy, even though the object as a whole doesn't have any what we would call kinetic energy in that sense. It's still got all this internal energy within the substance. All the molecules and atoms that make up everything in this truck are still all vibrating and still all moving and still all rotating and still all extending their bonds and all of that kind of stuff, right? So there's all this energy inside the truck, even though when we look at the truck in a kinematics or a mechanics sense, we might say it's got no velocity, therefore it's got no kinetic energy. So it's important to keep in mind that things can have no energy in that sense, in the mechanics sense, but still have a lot of energy in the thermal physics sense. Just in terms of language, it's important to realize that substances don't contain temperature. We say that they contain internal energy, and then we talk about temperature as being a measure of the translational kinetic energy, which is part of the internal energy, but we never say they contain temperature. You can't say an object contains 20 degrees Celsius. You can say that it is 20 degrees Celsius. 20 degrees Celsius is a property, it's a description of the average internal kinetic energy, internal translational kinetic energy of the atoms making up that substance, but you can't say that the that the substance contains 20 degrees Celsius. It doesn't make any sense that way. So we've defined internal energy as being the sum of all the energy, all those different types of energy that can occur inside a substance. Temperature is a measure of the average translational kinetic energy of those atoms making up the substance. What is heat then? Heat is the transfer of energy from one substance to another. So if you've got an object and you want to heat it up, you have to provide energy to it in order to increase its translational kinetic energy, or the average internal translational kinetic energy. You need to provide heat in order to do that, and that heat is the flow of energy, right? It's the flow of energy into or out of a substance. So an object cannot contain heat. You can't say that this object has a bunch of heat in it, because heat is the flow of energy. So heat is the flow of energy, then the object contains energy. So if you pour water into a jug, the jug contains water. You can't say it contains the pour. The pour was just the motion of the water into the jug. So heat and internal energy are terms that you need to understand. You need to be able to define them. Translational kinetic energy is the temperature of the substance. You can have internal energy, you can have temperature, you can have heat. They're all different things. So get used to the different terms and what they all mean. In terms of heat and internal energy, if you give a substance some heat, its internal energy must increase by that amount. If you pour 100 joules of energy into a substance, its internal energy must go up by 100 joules. But its temperature won't necessarily go up by that same amount. Right? The average internal energy, internal kinetic translational energy, is not going to get all of that 100 joules, because substances have different ways they can use it. It might put some of that energy into rotation, some into bonds, some into vibration, and some into translational kinetic energy. So that means that different substances, if you take two different items and you put 100 joules into one and 100 joules into the other, they might change temperature by different amounts, because they're putting different amounts of that energy into different areas of their internal energy. Thermal equilibrium is another term to learn the definition for, and that is actually just a physics way of saying that two things are at the same temperature. That's all it means. If you've got two solids in contact and they are different temperatures, then they will change energy. The colder one will gain energy from the hotter one. The hotter one will give energy to the colder one. So they'll change temperature. We'll talk about that a bit more in the next lesson, I believe, when we talk about thermal conduction. But they will change temperature. if you've all experienced this, you put something warm into a fridge, for example, it will cool down, it will become the temperature of the environment that it is in. When they reach that same temperature, that is when we just say they're at thermal equilibrium. So it's a physics way of saying that two objects are at the same temperature. That's all it actually means. Heat will always flow from a hot object to a cold one. Remember that this heat transfer is happening through molecular collisions. Hot objects have faster moving particles, cold objects have slower moving particles. If you get a slow moving particle and a hot moving particle colliding, then there's no scenario in which that hot moving particle, the faster moving particle, is going to gain energy from the slower one. It just doesn't happen. The faster one will give energy to the slower one, and that cools down the faster one and heats up the slower one. So the heat flow is always from the hot object to the cold object. There may occasionally be some energy flowing from the cold one to the hot one. If a cold one, remember that the temperature is all different. It's an average, so there might be a fast moving particle in the cold object and a hot moving particle, a slow moving particle in the hot object, and it might bounce, and the hot object might gain a tiny amount of energy from the cold one. But remember, there are so many of these collisions going that the overall average is going to be overwhelmingly energy going from the hot one to the cold one. Is it possible for a colder object to have, that English doesn't make sense, is it possible for a colder object to have more internal energy than a hotter object? Can a cold one have more internal energy than a hotter one? Absolutely. Remember that internal energy is a measure of the total energy to get something from 0 Kelvin all the way up to whatever temperature it is, whereas temperature is an average energy. So a very hot object, like a small red hot ball bearing, that has a high average internal energy, right? The average internal translational kinetic energy per atom in that red hot ball bearing is very high relative to the average internal translational kinetic energy of the water molecules in a big pool of water. Right? The pool might be quite cold, it might be 10 degrees Celsius, and the ball bearing is maybe up at 200 degrees Celsius. So the temperature, the average internal translational kinetic energy of all the particles in the ball bearing is much higher than the average internal translational kinetic energy of all the particles in the pool. So the averages are different. But if you think about the total internal energy, that's the total energy amongst all the atoms making up the object across all the types of energy that they can have. In the ball bearing, there are so many fewer atoms than there are in the pool that even though each atom has more, the total energy in that ball bearing is going to be less than in the whole pool, because the pool is huge. So even though each atom has less on average than the ones in the ball bearing, there are so many more of them that the total is greater. It's just like if you take 5 people with $100 and then you take 1,000 people with $5. Right? The 1,000 people with $5 have a total money of $5,000, whereas the 5 people with 100 only have 500. So the lots of people with less money has more total than the few people with more money. Right? Same thing here. The big pool, lots of atoms with less energy have more total energy than small thing with fewer atoms, which might happen to have more energy. So important to keep that in mind. Total internal energy can be greater, but the temperature is the thing which is the average of those kinetic energies, and that's the thing that determines which way the energy flows. So if you drop that ball bearing into the pool, because each of its atoms are warmer than all the atoms in the pool, on an individual collision scale, so the ball bearing atom and the pool atom colliding, the energy is still going to flow from the ball bearing to the pool. So the temperature difference is what determines the flow of energy. Even though there's more internal energy in the pool, it's still going to gain more from that ball bearing because it's the temperature that determines the flow of energy. Heat is just energy being transferred, so heat is just joules. We've already met joules, we've already met energy, nothing new there. It is joules. Same thing with power. We've met power. Heat is the flow of energy, how much energy moved. If you want to know how long it took, you want to introduce time into it, then you need to move into power. And as we saw before, that is measured in watts. So everything's all the same as we've already seen there. This is a rather outdated term calories, not for a food science sense. If you're looking at nutrition and food, then calories are still pretty common, but in terms of physics, we don't really use calories much anymore. Calorie is the calorie differs between capital C and lowercase c. We're used to using things like joules and kilojoules, where we put a K out the front to mean 1,000 times bigger. For calorie, for some reason, the people that invented the term decided that lowercase calorie would be one value and uppercase calorie is like a kilocalorie. So there's that distinction to be aware of as well. When you look on a food label, you'll see that calories are often in capital C, so they're actually kilocalories with a lowercase c. That's one thing to be aware of. But the calorie, lowercase c calorie, is the amount of energy needed to increase the temperature of 1 gram of water by 1 degree Celsius. So if you just take 1 gram of water, so that's 1 mil of water, one tiny little amount of water, and you give it 4.184 joules of energy, then its temperature will increase by 1 degree Celsius or 1 Kelvin. As I said, we don't use this term much in physics, but it's this idea is something that we'll expand on in just a moment. So 4.184 joules is 1 calorie, and 4,184 joules is 1 calorie with a capital C. So that's what a calorie is. It's just a unit of energy. So it's just if you ever need to convert between them, if you've got some number of calories, multiply by 4.184, and that's how many joules you've got. So that idea that I just mentioned about taking 1 gram of water, giving it 4.184 joules of energy and the temperature increasing by 1 degree Celsius or 1 Kelvin, that is a specific heat capacity. So that's what we're going to look at now to finish off this lesson. When an object receives heat, it ends up as all the different types of internal energy. That's what we're saying. You can give it energy, but it might put some into translational kinetic energy, which is the temperature change that we're talking about. It might put some into bonds. It might put some into rotation. It might put some into vibration. The temperature, the thing that we monitor, the thing that we can measure, is just that one type of internal energy. We don't really care about the others. They still exist, and they affect how much the temperature changes by, because if you put all the energy into the other ones, then the temperature is not going to change at all. So the other energies are still important, but they're not what we measure, and they're not what determines that flow of energy as we saw with temperature. So how much of that energy ends up as translational kinetic energy depends on what the object is made of. If you put it into one object, it might put most of it into translational kinetic energy. If you put it into a different substance, it might put only a tiny bit into translational kinetic energy. So putting the same amount of energy would mean that the two objects gain different amounts of temperature, even though they've both gained the same amount of internal energy. For example, if we give 1 gram of water 4.184 joules of energy, its temperature will increase by 1 degree Celsius. That's what we just saw with the calorie. But to heat up 1 gram of aluminium by 1 degree Celsius only takes 0.91 joules of energy. So you only need to give a gram of aluminium a quarter or less than a quarter of the energy you would need to give a gram of water. And that's because the aluminium puts most of its energy into that translational kinetic energy, whereas water puts a lot of it into things like vibrations and rotations because they've got those H2O molecules. Whereas aluminium is just atoms in a big grid because it's a solid, so it puts most of it into just heating up, just getting more of that jiggling, more of that internal kinetic energy. It takes more energy for water because it puts more into those other types of energy. So the specific heat capacities are different. So that's all a specific heat capacity is. It's just an indicator of how much of the internal energy you give a substance ends up as that translational kinetic energy, ends up as that temperature change that we are looking for. So that is what specific heat capacity is. And there's no real way to calculate that. You can't just look at a substance and go, oh, this is made of silicon and oxygen, so it's going to have this specific heat capacity. You have to basically experimentally determine it and come up with big lists. And so people have done this, and there are data tables on the internet that you can look up if you're interested. There are just big lists, and it says different substances, here's your specific heat capacity for that substance. The units for specific heat capacity, you can pretty much tell that from the definition. The specific heat capacity is the amount of energy needed to heat up 1 gram or 1 kilogram, if we switch back to SI units, 1 kilogram of matter by 1 Kelvin. So the standard units are joules per kilogram per Kelvin. How many joules per kilogram per Kelvin? But it is common to see variations. So often you'll see kilojoules instead of joules, or grams instead of kilograms. But degrees Celsius and Kelvin, as we've already said, are going to be the same, because we're talking about a temperature change. We're talking about changing by 1, 2, however many degrees Celsius. That's the exact same step size on the Kelvin scale. So when we're talking about specific heat capacity, we are usually talking, or we're always talking about a temperature difference. But there may be problems where you're actually using both actual temperatures, specific definite temperatures that you need to convert, and temperature differences that you don't need to convert. So do be very careful with all of that. Here's some examples. Gold, 130 joules per kilogram per Kelvin. So this is the amount of energy you need to take 1 whole kilogram of a substance and heat it up by 1 Kelvin. So for gold, you need to give it 130 joules. For mercury, 140 joules. Aluminium, 910 joules. For olive oil, it's 1970 or 1970 joules. Seawater, just under 4,000, and fresh water, just over 4,000. So those are just a few examples, obviously. There are many, many more different materials than that. If we give you a problem, we'll always give you the specific heat capacity for it. But if you are looking up some other scenario or something out of interest, then you can just Google it. There are a lot of reference tables. It can be difficult to find, and you can find that information that way. If you are stuck and you really want to know something, feel free to email me. I'm happy to help look up other terms or other values. One thing to be aware of if you do go online and look up values is that technically a lot of these values will change slightly as the temperature changes. So cold gold might put more energy into translational kinetic energy, more of its heat into that. So it might have a slightly different specific heat capacity than warmer gold. So a lot of them do change slightly as the temperature changes, but the changes are usually pretty small, and they're usually beyond the precision we care about in this course. So for our purposes, we will generally treat one substance as having a constant specific heat capacity while it's solid. Then obviously it'll be different when it's a liquid, because it's now a different substance molecularly. But for the whole time it's a solid, the whole time it's a liquid, or the whole time it's a gas, we'll generally just treat it as having one specific heat capacity. Water has a relatively high specific heat capacity, as you might have just noticed. The other materials were lower. Even olive oil, which you might think might have been similar, that's down at 2,000 versus water's 4,000. So it has a high specific heat capacity. That means that you can give it a lot more energy for a lower change in temperature. So if you've got a kilogram of oil and you give it 2,000 joules, it's gone up 1 degree Celsius. If you've got a kilogram of water and you give it 2,000 joules, it's only gone up 0.5 degree Celsius. So that means that water is very good for cooling things down, because it can take more energy off another substance in order to cool that substance down, and the water doesn't get as hot as a different material would. So that means that if you've got a hot object, you put it into water, the water gains energy off the hot object, the hot object cools down, the final temperature of that water will only be half as much as it would be if you put that object into oil in order to cool down. So water is very good for cooling. Unfortunately for us, with a lot of electronics, water is also bad for conduction reasons. So you got to be careful with that, but it is good in general for cooling things down. So that's the end of this lesson. I realize I didn't go into too much detail with specific heat capacity at this stage. We've mentioned what it is and how to calculate it and define the units and all of that. We will come back to that in lesson 24. The second half of lesson 24 will be another one of those example sessions where I just have a few examples and I work through them. The reason I'm leaving that until lesson 24 is that we're going to look at phase changes as well. So we're going to talk a little bit more about thermal physics in general. And then at the end of the third lesson on thermal physics, we'll tie that all together with a few examples on calculating heat changes and energy.